Now we'll proceed with Chapter 1, Algebraic Fundamentals, Section 1.1, Sets and Numbers, and the first little section of this on sets and relationships between sets and operations on them. Perhaps the basic concept in mathematics is that of a set, an unambiguously determined collection of mathematical entities. A set can be specified by listing its contents. For instance, the set A is W, X, Y, Z, or by describing its constants in any other way, so long as the members of the set are fully determined. For instance, the set of all prime numbers. Among all sets, the strangest is no doubt the empty set, traditionally noted by this symbol. The set that contains nothing at all. So, the set of the empty set containing no elements. This set should be approached with extreme caution, since it can readily sneak up unexpectedly as an exception or counterexample to some mathematical statement if the statement is not carefully phrased. There's a generally accepted standard notation for dealing with sets, and it should be learned freely. That a set A belongs to another set, big A, is indicated by writing A as an element of A, and that B does not belong to a set A is indicated by writing B as not an element of A. If a set A is a subset of set B, if whenever A is in A, then it also is the case that A is in B. And the condition that A is a subset of B is indicated by writing A is a subset of B or B is a superset of A. There is some variation in the usage, however, usually this indicates that the case of A equals B is allowed. However, some people will not do that. If it's the case that there's some B for which B is an element of B, but B is not an element of A, then you say that A as a subset of B is a proper inclusion, and it's denoted using these symbols if you want to be precise. In addition, we say that the empty set is a subset of any set A. Sets A and B are said to be equal, denoted by A equals B, if they contain exactly the same elements, or equivalently, if both A is a subset of B and B is a subset of A. From here, we consider the intersection of two sets. If we have the intersection of two sets A and B, which we denote A intersect B, we are considering those elements that belong to both A and B. Additionally, we have the union of sets A and B, denoted by A union B, which consists of those elements that belong to either A or B, or both. More generally, you can expand these to any collection of sets A sub alpha, where the intersection and union of these collection of sets is defined as follows. The intersection over all alpha of A alpha is a set of all elements such that A is an element of A alpha for every alpha, and for the union, the set of all elements A such that A is in some element of your collection of subsets, so some A alpha. We say that two sets are disjoint if A intersect B is the empty set. These two relations are related by De Morgan's laws, or just De Morgan's laws will come later actually. These are simply operations on sets, namely that the A intersected with the union of B and C is the same thing as the union of A intersected with B and A intersected with C. Additionally, A unioned against B intersects C, same thing as A union B intersected with A union C. Now we can come to the difference between two sets, denoted A subtract B or A without B, which consists of those elements A such that A is an element of big A, but A is not an element of B. It does not matter whether or not B is a subset of A. Additionally, we have the empty set, subtract the empty set is the empty set. Difference, like subtraction, respects order, so it matters what order you write them in. However, there's also the symmetric difference between two sets, defined as A symmetric difference B is equal to B symmetric difference A, which is A except B union with B except A, which is the same thing as A union B except A intersected with B. This is useful to illustrate using a Venn diagram. Additionally, we have the De Morgan's laws, which is that A without B union C is the same thing as A without B intersected with A without C, and A without B intersects C is the same thing as A without B union with A without C. As long as all of these sets are viewed as a subset of an ambient set E, it is understood that E without A is just denoted as A except as without A or the complement of A, and this is called the complement of a subset A. This simplifies De Morgan's laws and says the complement of A union B is the complement of A intersected with the complement of B, and likewise, the complement of A intersect B is the union of the complement of A and the complement of B. You may find it useful to write out the proofs for these, or you'll see them soon. Thank you.